Hello, thanks. First of all, I would like to start by thanking the organizers for uh, giving me this opportunity to present the work, and it has been a wonderful experience in here. So today I am going to speak about anomalous transport at band edges. Um, so before I start, so I'm basically from ICTS, International Center for Theoretical Sciences, part of TIFR, and and our institute has many resemblances with IBS actually. So there are lots of programs, and I welcome all of you to visit Bangalore. So before I start, I just wanted to say that so I have a couple of postdocs and students and a project student, and I'm broadly interested in open quantum systems, non-Hermitian systems, and low-dimensional systems, and also interested in integrable systems and some topics in mathematical physics, field theory. So let me start by presenting with the talk. So today I'm going to speak about transport in anomalous transport, and I will explain the meaning of what I mean. And this is the work done in collaboration with Madhumita Saha, Archak Purkayastha, and Bijay Kumar Agarwala, and the works are available here. So after giving some background and motivation, I'll talk about connections between transport and transfer matrices. I'll define what I mean by these by transfer matrices here, and I'm going to talk about anomalous transport and its reason coming from transfer matrices, and then I'm going to talk about addition of probes and something which we call super ballistic behavior. So let me start with the simple setup. So let's imagine this general setup. So the general setup is this thing that you see in the center. This is the system. And we are just coupling the system to some reservoirs. This is at zero temperature, so the reservoirs are at slightly different chemical potential. So this is a very general setup. And HS refers to this system. So now, for this purpose of this talk, we are going to discuss conductance. So I'm going to talk about conductance, which is basically defined in this way, and the nature of the system, and I'm basically going to focus on how the conductance scales with the size of the system. By the size of the system, I mean size of this HS. So, uh, so if the conductance, if this thing is independent of n, then we call it ballistic transport. If this is exponentially suppressed in n, then we call it localized or perfectly insulating. But if it is 1 over n power something, then depending on this value of this exponent delta, we either call it super diffusive or subdiffusive, and when delta is equal to 1, it is the conventional diffusive behavior. So this is basically, so the nature of the transport and how it changes with system size tells you a lot about the underlying system. So this is we just have to keep this in mind, and anything that is other than, let's say, ballistic, exponentially suppressed, or conventional diffusion like 1 over n, we will call it anomalous at the moment. Okay, so let me so please feel free to ask questions. So let me start with some properties of the closed system. So completely ignore these reservoirs. So completely ignore these oval shaped things. Only focus on the system. So let us consider a very simple setup, which is a tight binding model. And what I'm going to present today happens actually for extremely simple system, the simplest system you can actually think of. So let's focus only on the tight binding model here. So this is the tight binding model here with some on-site energy and hopping. So I'm only focused on the isolated part of the system. Now this is like a discrete Schrodinger equation for nearest neighbor tight binding model, and you can write it in this way. And you can recast this discrete nonlinear Schrodinger equation as a transfer matrix problem. So this is what I mean by transfer matrix. It just moves psi I minus 1 to psi I plus 1 psi I. So essentially this is the transfer matrix. Now this plays a crucial role in what I'm going to describe. So as of now we have not done much. We have just studied, we have introduced this matrix, 2 by 2 matrix. We just transfers in some sense psi I minus 1 to psi I plus 1 psi I. So with EI plus Q equal to EI, Q is the length of the unit cell. So this is just the length of the unit cell. For a large part of the talk, you can assume that the unit cell is just 1. So you can assume Q is 1. So what is this transfer matrix doing? For example, this is the dispersion relation. If I take trace of TQ, that will be omega minus epsilon I equal to cos 2 cos k. So basically just this equation here gives me the dispersion relation. These are the eigenvalues of the transfer matrix, and this matrix is non-Hermitian. Okay, so the transfer matrix is non-Hermitian. And at the band edges, k equal to 0 plus minus pi, these eigenvalues coalesce, and band edge is an exceptional point of the transfer matrix. So as of now, I have not said anything about the reservoir. So forget transport, just focus on this 2 by 2 matrix and the eigenvalues of this transfer matrix, and the fact that something special happens with this transfer matrix at the band edges. Okay, so you put k equal to 0 or plus minus pi, and you will see that. So I have tabulated it here. So this is t of mu. This t is when mu is at the band edge, then this is an exceptional point. When mu is outside the band edge, you will get the eigenvalues are real, and then when mu is within the band edge, then it is eigenvalues are complex. So this simple transfer matrix sort of has some sort of PT transition, and at the band edge. So here, just to recall, the band edge is at k equal to 0 or plus minus pi. So the band edges are at plus or minus 2. Okay, so at the band edge you have an exceptional point. So this is the property of the transfer matrix. So now you may ask, what is this anything to do with transport? So that is what I'm going to discuss next. So now we connect the first site and the nth site to a fermionic chain, which is modeled by infinite number of fermionic modes. So this is an infinite, semi-infinite model of tight binding chains, or basically infinite model of fermionic modes, and there's an infinite model of fermionic modes, and we are interested in linear response conductance. And the conductance at 0 temperature within the linear response is given by this formula. Okay, so this is just setting up the problem. So this J's here are the Barth spectral function, and this delta 1 comma n, this is where the information of transfer matrix actually enters. So this is the conductance. Okay, so this is the formula again. This is called transmission. These are the Barth spectral functions. That depends on the details of your Barth. And this is where, yes. Yes. Both the Barths are at 0 temperature, but they are slightly different chemical potential.
Just for people on Zoom, can you repeat the question?
Okay, yeah. So my question is, isn't our bath is at 0 temperature?
Yes. Both baths are at 0 temperature, but they are slightly different chemical potential. Mu and minus delta mu.
Okay.
Mu and mu minus delta mu.
Okay.
Yeah. So we are looking at 0 temperature conductance and in linear response because delta mu is small.
Okay, I got it.
Yeah. Thanks. Okay. So now, so this is this formula. I mean, this is very standard, but and keep in mind that we are after all interested in the system size scaling for this talk. So you can So wherever you see system size, your focus should be there. So here delta 1 comma n actually happens to have these relations. Delta 1 comma n basically is determinant of some matrix, and delta 1 comma n has this relation where the transfer matrix that I discussed enters here. Okay, so and this q is the band index, but you can assume that there's only one band. Now the system size scaling of conductance is independent of the type of the bar spectral function and is entirely governed by the nature of transfer matrix. So this n, so small n here is basically capital N by q. So assume q is, I shouldn't have, I should have probably talked about just one band, but assume that you have unit cell with, you have just a single unit, this thing. So small n is basically capital N. So you put a capital N here. Okay, so this is tq of mu power n. So now you can say that once I know how this thing depends on n, then I can ask how this denominator depends on n, and then I can ask how conductance depends on n. Okay, so that is the plan. So recall again that if g was independent of n, it is ballistic. If it is exponential in n, we call it perfectly insulating, and if it is some power law, then it is either super diffusive or subdiffusive, with diffusing being delta equal to 1. Okay, so now let's go back to now everything here, the n dependence essentially comes from here. Okay, this is where the n dependence is hidden. So so now at the band edge, so now let me talk about what happens at the band edge, because that is the most interesting thing. At the band edge basically means that we have this tight binding model and the dispersion relation was 2t cos k. So the band is -2 to 2. What happens if I put mu equal to 2 or -2? Okay, what happens if my chemical potential is exactly at the band edge? So at the band edge, the transfer matrix cannot be diagonalized. I said it's an exceptional point, and it can be taken to Jordan normal form. These are details, but most important thing is this expression here. The transfer matrix power n is nothing but this. You can show that this is this transfer matrix power n is this. So n is here. Okay, so the n is here. So going back to this expression, you can see that delta 1 comma n is n. Okay, and because delta 1 comma n is n and the conductance was here, you basically get the conductance scale as 1 over n square. Okay, so we have some very strange situation where you have a simple tight binding model and the transport across the tight binding model at the band edges is subdiffusive. So this is very strange because the system is quite clean. Usually to have anomalous transport you need something exotic, or you need to have some interactions and so on. But here we get subdiffusive transport in a very simple setup. Okay, so typically you would expect if you have an integrable quantum model and you study transport, usually things should be just ballistic. Or if you have a non-interacting system at the center and you couple it to baths, typically conductance becomes independent of n. Okay, so this is the important result, that conductance goes as 1 over n square, and this is purely coming because of this relation, which only happens at the band edges. And by analyzing the transfer matrix, so by analyzing this formula, you can easily show that outside the band, the conductance is exponentially suppressed. If you're within the band, it is ballistic, and if you're at the band, it is 1 over n square. So this is what I wanted to show here. So before I showed this part of the table, but here now I show the conductance. If mu is within the band, so if mu is within the band edges, like 1.5 or something, then the conductance is then you have ballistic transport. If you are outside the band, then you essentially have localized. It's just transport is highly suppressed, and at the band you have 1 over n square. So essentially, what happens here? You seem to have some sort of phase transition as you tune mu, and this is very similar to the kind of transport or properties that happen in certain quasi-periodic systems. But I'll not get into that. The important point here is that as a function of mu, you have a phase transition, even in the most simple example that you can think of. So these are basically the results with and this, of course, here the method is exact. There is no approximation. It's a simple enough problem to solve using non-equilibrium Green's function method, and you see that these are the eigenvalues of those transfer matrix. This is two band case, so Q is equal to 2, and you see that at band edges the eigenvalues are colliding, and so on and so forth. Important point is here, this plot, second plot, where you see that inside the band, you see that it is independent of n, the conductance, and outside the band, it is exponentially suppressed. And in these plots, this is at the band edge, okay, because we have two bands here, so we can choose one of the edges. You see, we have perfect 1 over n square anomalous transport at the band edges. This is outside the band, E2 plus 0.1. So you're just above the upper band, so to say. And you see that it is exponentially suppressed, e to the minus something times n. And inside the band, you see basically it is independent of n. So this is the and this can be generalized to n bands and so on and so forth. So now I'm going to discuss the next part, where we ask what happens if you subject it to environmental effects. So till now I discussed this part here, where you have a left lead, right lead, both at 0 temperature and slightly different chemical potential, and you have a system in between. And we studied anomalous transport in this direction. But now you can ask, what is the role of non-Hermitian properties of the transfer matrix on environmental assisted transport? So what we are asking is, so the superballistic scaling of conductance with system size has not been reported before. So what we are going to show here is that we get something called superballistic transport, and I'm going to explain what it means. And unlike the presence of, unlike the spread of initially localized wave packet, this feature crucially requires the presence of incoherent effects from surrounding environments, and therefore cannot be seen in an isolated system. So basically what I'm going to show here has no analog, at least to what we understand, in the isolated system. So we are going to use Buttiker voltage probes. So basically these are additional baths, these are voltage probes, and they are such that there is no average particle current. So these are baths which are fine-tuned in such a way that there is no average particle current, and these kind of probes are supposed to mimic interactions. They are supposed to mimic incoherent effects essentially. So you basically have your main thing here, but you connect it to many tight binding models, but make sure that there is no loss of current. So effectively what it does, it takes care of some incoherent effects. So suppose you put this, we seem to get very interesting results. So we have this, this is the setup, and I have this chain which I call HC, which is just my tight binding model. And then I have left and right leads, which was the main thing. And then I have this PNs, these are the probes. So these are N probes. This is the chain coupling to the left lead. This is the chain coupling to the right lead. And this is a chain coupling to the probes. Okay? Yeah. Oh, sorry. Okay. Okay. So 5 minutes for 20 minutes or?
5 minutes, we are at 20 minutes. So
Okay. Okay, yeah. So I'll here the only thing you have to focus on is this tau p. So you can keep an eye on this tau p, and this is again beta infinity, zero temperature case. Okay, so now we are asking what happens to this transport. So we see something quite interesting here, and which we sort of understand. We have some reasons, and in addition to exact numerics, we also have some reasons. Um, so So in the non-equilibrium steady state, there is a flow of current from source to drain. There is a flow of current. By construction, there is no average current flowing into the probe baths. This is by construction. The presence of these probe baths, however, crucially alter the transport properties. So these probe baths, although they don't take particles and so on, the net particle current is zero. They still completely alter the transport properties. And we describe the non-equilibrium steady state of the system via non-equilibrium Green's function techniques. So what usually happens with these probe baths in the thermodynamic limit is that it makes everything diffusive. It makes everything conventional diffusion. So you take something which is in the ballistic regime, you add these probes, so the conductance goes as n power 0, but when you add these probes, the conductance becomes 1 over n. So this is what happens when you add probes. Effectively, you are making the system interacting and chaotic enough such that it behaves like a regular diffusive system. That is the philosophy. So we can do this Green's function method and so on and so forth. And again, there is some version of transfer matrix. T0 is the transfer matrix, so there is some addition to the transfer matrix and so on. But I may not be able to go into the details. But let me just show the plot. So the plot. So in this plot, what we see evidence of super ballistic scaling. So what I mean is the following. So let us focus on the top left plot here. And tau. Remember, I said we should think about tau. Tau is nothing but how the main system is connected with the probes. So let us look at some value of tau p. Let us look at the green thing here. So what happens is initially we have some 1 over n square. This is n. The x-axis is n. Then what happens is that we get something which goes even faster than n power something. So we call this super ballistic scaling. So we get n power. These are the exponents we get. And so we have something that increases with system size. So this is a very unexpected thing. Of course, if you keep on increasing the system size, eventually we expect it to become 1 over n. But there is a significant decades of system size where we see super ballistic scaling. So we see evidence of super ballistic scaling, which means that g of omega g goes as n to the phi, where phi is greater than 0. It is more than ballistic. And you can see similar plots at large tau p. If I increase tau p too much, what happens is that the super ballistic zone becomes shrunk. So if I increase tau p too much, the system becomes diffusive very soon, which is understandable because tau p is making it too incoherent, and eventually it becomes diffusive. But if I reduce tau p, I have significant super ballistic region. And this is literally the last plot here is basically the size of the super ballistic zone as a function of 1 over tau p. So if tau p is large, then the size of the super ballistic zone is small. But if tau p is small, 1 over tau p is large, and the size of the super ballistic regime is large. So what we see is that there is a significant region where I increase the system size and my conductance becomes better. And this is because of very delicate interplay between non-Hermitian physics of transfer matrices and its interplay with the probes. So this is this is one of our main results where we see super ballistic scaling. In other regions, what happens when you add probes is eventually things become diffusive. So if I have a system which is ballistic and I have ballistic transport, you add probes, eventually it will get diffusive. If you start with something which is highly localized transport, you add probes, it will again become diffusive. So everything will tend to diffusive, but here what happens is that before it becomes diffusive, it becomes super ballistic and then goes down. Okay, so to conclude, we have shown how non-Hermitian transitions in transfer matrix of Hermitian Hamiltonians. So when I said transfer matrix, I mean transfer matrix of the Hermitian Hamiltonian. I did not talk about the baths in my first slide, right? And then we studied how this affects the nature of quantum transport. We united two sort of different concepts: the symmetry of transitions, symmetry and transitions in non-Hermitian matrix. The transfer matrix undergoes a transition from complex eigenvalues to real eigenvalues through an exceptional point. And we connected that concept to band structure and quantum transport in fermionic systems. And completely different way, so subdiffusive scaling of conductance with a universal exponent can originate. That is from exceptional points of transfer matrices. We showed 1 over n square scaling, subdiffusive scaling. And the probes, the environment, which are modeled by these well-known Buttiker probes, are such that at every band edge, there's an interplay between transfer matrix exceptional points and weak incoherent effects from the probes, and this leads to power law increase of conductance with system size. And so this is fascinating environmental assisted super ballistic scaling of conductance seen over finite regime of system lengths. Thanks.
Thank you very much. We have few minutes for question. Yeah, Giuliano.
Yeah, do you have any idea what would happen if you consider thermal transport? I'm asking this because maybe you can have violations of Tiedemann-Franz law, something like that, or not.
So, okay, thanks. That's a very important question. So, so what happens when you add, for example, slightly non-zero temperature, is that the system, the bath starts getting access to many energy levels, right? So then what we expect is eventually it will start becoming ballistic. The transport will become ballistic because now we don't have a sharp Fermi function. So the expectation is that if you add even a bit of temperature for long enough system sizes, eventually you will see ballistic transport. So yeah.
But do you have any feeling about thermal transport? I mean, about you compute heat transport. If you do you have any idea what would happen? Probably this effect is not there, or.
Yeah. So currently, my feeling is that effect is not going to be there, but I need to think about it a bit more. I mean, we might have to do a few more things to see if we can get some sort of anomalous heat transport. Yeah.
Sir, I think this is just a baby question because I think I completely missed. So this is just a free fermion, right?
Yes.
So this is a very basic question, but why is the transfer matrix non-Hermitian?
So that's how, I mean, so we just call this the transfer matrix. So you see, this is the free fermion model. Right. This is a discrete Schrödinger equation, and just we rewrite it in this form. The same model, you just rewrite it in this form, and this 2x2 matrix is just non-Hermitian.
Right. I see.
So yeah. So it's just.
So there's a difference in the description. So.
I mean, the thing is, it is useful to introduce this. You don't really need to introduce this, but right. If you introduce this and connect it to transport, and use the fact that this simple matrix has exceptional points, then you can rigorously argue 1 over n square. But if you did not introduce transfer matrix, you can just do the exact NEGF calculation and show that you get 1 over n square.
So in the simulation, did you just do the brute force?
Absolutely.
I see.
The simulation is brute force, but we wanted to know why we are getting 1 over n square, because that is very strange.
I see.
And so that is the.
Okay, interesting. Thank you.
Thanks.
Okay. Very quick, eh?
Do you have any control over the type of probe that you use? Or
Yeah, so we need we need probes such that we don't have net current, but there could be some other versions of probes, and it's not clear whether we'll get super ballistic scaling there. But this is probably the most common probe that is used. So that's yeah.
Okay, I think you are going to say, okay, yeah, let's ask.
So the simple question is this epsilons or the on-site potentials, what are the difference like in the bulk or at the boundary? Is there any difference?
No, so here because we have to connect it to the baths eventually to study the transport, we really we cannot have periodic boundary conditions. So we have an open chain coupled to the baths at the edges. No, it'll be same. So you have epsilon 1 to epsilon n, and they are all same. Yeah.
Okay, thanks. Time to switch the speaker. Are you going to speak?
Yeah, one remark, sorry.
Oh.
Yes, thank you for these interesting results. But of course, before planning a laboratory experiment, I would check this effect by using the alternative approach of the master equation. Because to be sure that this is not the artifact of the Putiker formalism which you use in your analysis. But we can discuss this later on.
Sure, yes.
Yeah, I agree that it's time to move to the next speaker, who is Andrei.
Thank you.